In this video, I'll be discussing about the properties of phi n function, that is Euler's phi function. And we know what is the phi function. So before I start, let's me to define what is phi n. Phi n, this consists the number of positive integers strictly less than n that are relatively prime with n, that are relatively prime with n. So in the set form, we can also say phi n, this consists of the cardinality of the set, which consists a number m such that this number lies between strictly less than n, and even if we want to include equality, we may include, but the condition is that the GCD between m and n should be 1. So this talks about all positive integers strictly less than n or even less than equal to n. Now the very first theorem that we want to prove here is the theorem which is due to cos, and that's a very interesting property followed by the phi function. So this theorem says that for each positive integer n, greater than or equal to 1, summation of phi d, where d is the positive divisor running over n, that is equal to n. And a very interesting property, recall, we have done a similar property with the Mobius function. A similar property was with mu n function also. And what was the property? That if we sum mu d, where d runs over all n, this takes the true value, either it is 1 or it is 0. And here if n is equal to 1, this value is 1. And here if n is strictly greater than 1, this value is always 0. So we have already done this result also in the last class. And now let's prove this property for the phi n case. Now there are two proofs which can prove this theorem due to Gauss. So let me to take the first proof. And the first proof use the concept of the multiplicative. So first proof, and this use the concept that phi is a multiplicative function. So in my last video, we have already discussed about the fact what is the multiplicative function and how the phi is multiplicative function. And let's now move further for proving this case. Now we are proving this case for n is equal to 1. If n is equal to 1, then the summation d divides n phi d. This simply turns out to be summation d divides 1 phi of d divisor. So here 1 has only one positive divisor, that means the summation runs over 1, and phi of 1 is 1 by definition, so which is equal to 1, because we have considered the case n is equal to 1. So result holds. So result hold for this case. Now for n is strictly greater than 1. Okay, so now we consider the case when n is strictly greater than 1. In that case, we also consider a function fn. So let's consider a function fn, and this is what we want to calculate, phi d divides n. So this is what we actually want to find. And in the theorem, we see, if we look at the star, if we look at it, equation number 1, we can see from here that we want to show, so you may even write here, we want to show here that fn turns out to be 1. Okay, so to show fn is equal to 1, if we look at equation number 1, it is very clear. Now how do we prove? So take n is equal to, because n is any positive integer, so take n to be in its canonical form. So if I consider p1 up till pr kr, that's the canonical form representation. And now if I write fn, what it will become? It will become f of p1 k1 up till pr kr. Okay, and this is same as f of p1 to the power k1 up till so on f of pr to the power kn. And here that means I have used the concept that f is multiplicative. So from here, as phi is multiplicative, so this implies capital F is multiplicative. So I'm using this fact that if phi is multiplicative, f is multiplicative, so this equation number 1 holds very, so this equation number 2 holds very obviously. So this equation number 2 holds very obvious result. Now once this equation number 2 holds, so I also want to know what is individual of these quantities. So for a particular I, so for particular I, if I want to calculate what is f of pi to the power ki, so by definition what is function? So this means d divides pi to the power ki phi of d, because this is how we have considered our function fn. So now in place of n I have p to the power ki. This means if I just simply open, divisor of pi to the power ki is what? Divisor 1, and then pi itself is a divisor, and then we have pi square and plus so on plus phi of pi to the power ki. This is the last divisor. Okay, now phi 1 is, we already know 1, and by formula we know what is this. This is pi minus 1. We know what is this. This is pi square minus 1 less. This last term is nothing but this is pi to the power ki minus pi to the power ki minus 1. So we know we are using here, use the formula. We have already proved this formula that if we have p of pi to the power ki, this is nothing but it is pi to the power ki minus pi to the power ki 1 less. So this is the formula that we are using here in this step. And once we use this formula, we see here everything is going to cancel. This one is cancelling with this one, this pi is cancelled with this pi. So, and that means in the bracket the second term get cancelled. This means this term will be get cancelled with the previous. So the remaining term is pi to the power ki. So if we look at the left hand side, so this means if we look at the left hand side, pi to the power ki is equal to pi to the power ki. Okay, and so equation 2 becomes, so what does equation 2 implies? We had f of n and we had f of p1 to the power k1 up till so on f of pr to the power kr. So this means this will turn out to be p1 to the power k1. The next term will turn out to be p2 k2, and the last term turn out to be pr kr, and which is nothing but it's just an x. So we have proved that fn is n. So once fn is n, so this means what is our fn? Fn was nothing but it is summation phi d divides n, and that's is n, and this is what we wanted to prove. So that's the proof complete. So which proves? Now this is the first proof, and let's take now the second proof. So that was the first proof that we have considered here. So this was the first proof. Now in the second proof, I'm going to use a counting approach. So second, or we may say alternate proof. So in that alternate proof, so the first one we use the concept that the phi is multiplicative. Here it is based on, this proof is based on counting or enumerative approaches, enumerative arguments. So we want to enumerate a set and then we want to count that set for the this summation phi d formula. Now, so I'll write down here the argument, and then parallelly I'll take an example to explain this step. So what we want to show is, we want to show summation phi d divides n, this is n. So this is what we want to show, okay? And let's consider the set 1, 2 up till so on up till n, okay? Now in this set, to count phi n, in this set to count phi n, we must look at integers. We must look at integers which are relatively prime to n and less than n. Okay, so this means we want to count f phi n, so there should be we should be looking the positive integers within the set which are relatively prime with this n, and to do that, and to find above let us take d as a positive divisor of n, d as a positive divisor of n. Okay, and we put the integer m in the class st, provided that GCD of m and n is equal to d. Okay, so or we may say SD is a set which consists of m such that GCD of m and n is d and 1 less than m less than or equal to n. So suppose that we consider a set something like this. Now GCD of m and n, this is same as d if and only if GCD of m by d and n by d, this is same as 1. So the number of integers in the class st, so the number of integers in the class st is equal to number of positive integers. Of course, in the previous case also we are considering positive integers only. Number of positive integers not exceeding n by d that are relatively prime to n by d. So in this set we are considering the number related to n, and on this side we are considering the number related to n by d. So in other words, this number is nothing but it is equal to phi of n by d. So this number is something like this. So this means number of integers, so on this side we have again phi d number, and this side we have phi of n by d. So what we do is we get n is nothing but it is d divides n phi of n by d, and d runs over all positive integers. So this quantity is nothing but it is same as phi of I may call this as d dash, or you may call this as d, because this is same as a divisor only. Okay, so if you get confused, so you may put here d dash and then we may consider it as d divides n phi of d. Now let me to explain this theorem again a little bit one by one while taking an example here, so that the steps of enumerations are a little more clear to us what we have done. So what I'm doing is I'm considering an example parallel to this enumeration part. Now let us consider a set. Suppose I want to take a fixed number n is equal to 10. So the number is 10. So this means we have a set 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we got a last number 10. Now the numbers which are relatively prime to 10 are, what are the number which are relatively prime to 10 are? That is 1, 3, 7, and we got 9. Okay, so that's the initial number that we have, and we already know that phi of 10 is 4. So we know phi of 10 is equal to 4. Now how do we count this case? So in this first case what we are looking is you take a number d as a positive divisors of n. So what is a positive divisors of 10? So we consider positive divisors of n, and positive divisors of n, in this case n is 10. So the positive divisors of n are 1, 2, 5 and 10 itself. So in that case, and then we construct a set SD. So this D stands for positive divisor. So this means I want to construct the set SD. So this means I have a set S1, I must have S2, S5, S10, because this is based on the divisor. In S1, I want to put up the numbers from this main set, which is this one, those number where the GCD is D. So if I look where the GCD of m comma n is equal to 2, so the number should vary from 1 to n. That means the number should vary from 1 to 10, and the GCD of m and n should be equal to D. So this means in this set we'll have the numbers 1, 3, 7, 9, because the GCD of this number and 10 is 1. In the second step, the GCD of these number and 10 should be 2. So here, in this case, GCD of 1 and 10 should be 1. In this set, GCD of 2 and 10 should be 2. So because here, the m and n, whatever the number we'll keep here, whatever be the number we'll keep here, that should be 1. So we can keep the number 2, 4, 6, 8. All of these number GCD with 10 is 2. In S5, I want to keep the number m whose GCD with 10 is 5. So this means in this set I'll have only one number, that is 5. In this set I'll have a number whose GCD is 10. So that means the number 10 itself. Now in each set, if you look at this first set, now if I look at the first step, so if I look at the first step, what is this? This means here I'm considering phi of n by d. So phi of n by d, this means I'm considering phi of 10 by 1, and here the total number of the element I have here, the 4 element. So because I am considering phi 10. Similarly, in the next case, I am considering phi of 10 by 2. So I am dividing n by d. So because I am considering phi of n by d, so this number is again, we have 4. In this set, I am considering phi of 10 by 5. That is phi 2. Phi 2 will have only one number whose GCD is with 1. And in the last case, it is phi of 10 by 10. That is phi 1. And the phi 1 is this. So for the previous case, it is phi 2, which is 1. Now, if I sum these 1, so that's what the total number should give me. So if I sum this case, so what will happen? So if I sum d divides 10 phi of d. This is nothing but it is phi 10 plus phi 5 plus phi 2 plus phi 1. So this is 4 plus 4 plus 1 equal to 10. So that's the answer for the main case. And this is what the theorem says. If phi 10 divides this, phi of 10 is equal to 10. Or we may say summation d divides n, phi of d, this is same as n. So that's the theorem what we have already proved. Now you see here, first we have considered ST. Now to count the number of element in this set, what we have done, GCD of mn is equal to d if and only if md upon n by d is equal to 1. So we have considered now, we have divided the class into 4 where the GCD gradually turns out to be 1. So this means the number of integer in this class SD. This is same as the number which are in the class n by d and they are relatively prime. So that is phi of n by d. So this number is same as this number because phi of n by d is nothing but it is again a divisor. So that's the another alternative proof where the counting principle holds. But in case if we find it difficult, we may have a simple proof where the multiplicative portion is used. Now, so we have another now a theorem which again talks about the second interesting property of this phi function. And what does this theorem says? For n strictly greater than 1, the sum of the positive integers less than n and relatively prime to n is half of n times phi n. So let's prove now this case. It's a very interesting result again. Now consider Consider the set 1 to n, 1, 2, 3 up till n. In above set, let a1, a2, a3 up till so on a of phi n, these be the positive integers. These be the positive integers less than n and are relatively prime with n, and the GCD of ai comma n is equal to 1 for every I which lies between 1 and phi n. So I may write it like this. Okay, and we also know, now note here, so a simple property of the GCD we can verify. If the GCD of an is equal to 1, this will hold if and only if GCD of n minus a and n is equal to 1. So this is an obvious property. So this means from here, if this is a set, so this also implies that n minus a1, n minus a2, n minus a3 and so on, n minus a phi n. Okay, these be the positive integers less than n, and the GCD of n minus ai with n is 1 for 1 less than I less than or equal to phi n. So this is nothing but these two sets are actually the same set written in a different order. So we may say now we can simply add the set. These are the same number written in a different order. So we simply sum them, and from here you see how many times n is repeating. N is repeating phi n times, because the total sum here is for phi n quantity, and then we have minus a1 plus a2 plus so on plus a of phi n. On both sides we have the same quantity a1 up till plus a of phi n, which makes it twice of a1 plus a of phi n, and this is equal to n times phi n. And this implies if I sum these numbers, this is nothing but it is half of n of phi n. This is what we wanted to prove, that sum of positive integers less than n and relatively prime to n is half of n of phi n. So that means this result holds true. Now let's explain this. Let's explain this star remark if there is still some confusion in the star from the example. So what does this example says? Let me to consider a number n is equal to 30. If n is 30, what are the positive integers that are relatively prime with 30? And then we can find out this number. So the positive integers that are less than 30 and relatively prime to 30. What are these integers? This is nothing but this is 1, 7, 11, 13, 17, 19, 23, and we have 29. And if I want to sum these numbers, so summing these numbers would be 1 plus 7 plus 11 plus 13 plus 17 plus 19 plus 23 plus 29. If I want to sum this by formula, what will become? Half into n into phi n. So half into 30 into phi n. Phi n is 8. So this quantity will become 1. So this becomes 15 into 8. So we have 4 and then it becomes 120. So, and also if I want to see this property, so this is ai's, and if I want to consider n minus ai, so we see here if this is 1, so this means it is 30 minus 1, so that makes it 29. This is 7, so this is 30 minus 7, that makes it 23. 11 is 30 minus 11, so that makes it 19, and so on. 29, this is 30 minus 29, that makes it 1. So this means the star and the set that you will obtain here, this double star. So star is same as double star, written in different order. So that is why we have used this fact here by when I've written here this star, that if I sum this quantity or if I sum this quantity, they both are exactly same. And you can see this fact easily by this property, that the GCD of a comma n is equal to 1. So the GCD of n comma a with n is equal to 1. So that proves our this theorem also. Now in a very interesting result, we have another one theorem which connects phi n with the mu function. So what is that theorem? This says for any positive integer n, phi n is nothing but it is n times summation of d divides n mu d by d. And this is a very simple proof by the Mobius inversion formula. We know if I consider fn, take fn, this is equal to summation phi of d divides n, and we have just proved this theorem. So this is just proved in last case. Okay, so we have just proved this in the last theorem. So by Mobius inversion formula, so I'll take by Mobius inversion formula, so what will happen? It will give me phi n, this is equal to summation mu d capital F of n by d, and d divides n. So if I apply Mobius inversion formula here on this side star, so apply Mobius inversion formula here, and we should be able to get this. Now obviously fn is equal to ft, so this means this is same as d divides n mu d, and I can replace this quantity as n by d, because fn is equal to fn. This is already we have, and this proves the result.